name is Shaotran. I'm from the Edge Computing Lab at Harvard University, and I'm here to present GLADAS, the gesture learning for advanced driver assistance systems. So shown here is a self-driving car without GLADAS. Pedestrian says stop, and the car just continues to drive without stopping and just ignores the pedestrian. This is a big problem. Before we talk about how we solve these types of problems, let's first look at some of the research done in the field of self-driving. There are many different types of problems, but they can be separated into two distinct categories. First, there's more easy problems such as trajectory planning, and more of the complicated problems in the field that are not being currently focused on within the research base. These are things such as pedestrian interactions, city crowds, and bad weather. In specific, we focus on pedestrian interactions. And in specific, we focus on gesture recognition for pedestrian interactions. You can think of yourself as a car driver reaching an intersection, and at the same time, there's also a pedestrian there at the intersection. Now, the pedestrian might say, stop, let me go first, or, oh, go ahead, I'll go after you go. And in these cases, we can see that hand gestures are extremely important for self-driving cars to understand, because they happen all over the world. So today, we're going to implement GLADAS, which is a hardware-in-the-loop simulation framework for gesture learning research. In other words, we allow developers to create and test their own custom algorithms and their own custom hardware, and then have GLADAS test out how it performs within the simulation. In addition, GLADAS acts as a benchmarking system. Here you can see a video of a benchmarking system used for seatbelts, and you can see here that the federal government has used these seatbelts and shown that they can be benchmarked. In a similar way, we want to use GLADAS to benchmark the performance of gesture learning for self-driving cars. So GLADAS can be split up into three different parts. As shown in this video here, it consists of a simulated environment, a simulated self-driving car, and an image streamer. So this is GLADAS, and the first part is the simulation. The simulation, as you can see, is pretty realistic, and it's representative of real-world driving. In addition, because it's all on a computer, there's no risk posed to the public, versus if you were to actually do these experiments with cars and pedestrians in real life. Finally, because it's on a computer, it can be easily reiterated, and therefore it's great for collecting data and testing repeatable for thousands of trials. In addition, we have a simulated self-driving car. This is powered by AirSim, and it features an array of sensors, which we use the RGB camera for. Now, we use the RGB camera, and we're going to stream images from the car into our algorithm. The objectives for this image streamer is it has to be real-time processing, and that has to stream high-resolution images. In our research, it streams at 12.62 frames per second, and we can see and we have to note the architecture is extremely key to making sure that the streaming performance is as high and great as possible. Now that we have our GLADAS architecture, it's compatible with any custom GL system. In our research, we create and compose one basic dummy system to show the audience how this GLADAS framework can be used to test any GL system. So here's an example of one of the GL systems which we created, and then we tested to see how GLADAS performed on it. So the GL system is composed of an algorithm with a two-model architecture. One is a detector and one is a classifier. And these modules are put together to form our algorithm. Remember that this algorithm is just one example of a sample GL system that can be used. And we want developers to replace it with their own custom hardware designs and their own custom algorithms in the future. Now, our own example GL system has an algorithm detector. And the detector is going to take the image streamed frames from the self-driving car, crop it, and return just the chest to the head point of view. Now that we have that point of view, we split it into 32 temporal frames, and these frames then, because of this requirement, goes into a 3D CNN, and the 3D CNN is going to take these 32 frames and decide, is the gesture go forward, stop, go left, go right, and no gesture. These 5 gestures are commonly noted as the top 5 hand gestures used by pedestrians in previous research. Now that we have our GLADAS architecture and we have an example GL system, a basic dummy system, we can then use GLADAS to evaluate how well this GL system actually performs. We evaluate this through a couple of metrics. The first metric we use is accuracy. Now, accuracy in general tends to prioritize good predictions, and it disregards bad predictions. So we can see here that the formula here, and it's overly optimistic. On the other hand, we also use the metric of the F1 score. The F1 score, unlike accuracy, is another important metric because it penalizes false positives and false negatives more harshly. In other words, in the realm of self-driving cars, it's extremely important to notice false predictions that are bad predictions, because any bad prediction can lead to an accident, and we don't want accidents to occur. Therefore, we use both accuracy and the F1 score to look at our metrics. Now, we want to test the GL system in a couple of different scenarios. We test them in 4 different scenarios, and these 4 scenarios are commonly noted as the top 4 interactions between cars and pedestrians. Once we have these predictions and these scenarios, we can then evaluate how these GL systems perform in these scenarios, and this performance can be brought into the real world, because if it does well here, it would also do well, hopefully, in the real world as well, since these scenarios are realistic of real world driving. So for each scenario, we create a precision vehicle graph. In essence, a precision vehicle graph measures and displays a visual performance of how this classifier will do. Optimally, we want the optimal curve of the graph to be a box, as pretty much shown in scenario 4. In scenario 4, the classification from our GL system is almost perfect, but as we can see in the other 3 scenarios, it's not as good. However, in all 4 scenarios, it's still important to notice that the classification is over the baseline, so it's pretty good. We also showed common metrics. Accuracy of our dummy GL system is 0.946, and the F1 score is 0.859. These are metrics that are averaged over gestures in all our 4 scenarios, and it represents a sort of new standard for the performance of GL systems. In conclusion, our basic system is a great start so far, and this GL system is replaceable with future custom systems, configurations, and hardware designs that can even better the metrics that we saw here. GLADAS' benchmarking suite allows developers to then develop their own systems and see how their systems would perform within GLADAS. Finally, GLADAS enables a good GL research to prevent future common accidents from occurring. We want to enable the next future for GL research, and this allows cars in the future to not have to worry about bad gesture recognition. Thank you, and I'm open to any questions from the audience.